In this video, I'm going to go through some examples of reflections and even and odd functions. I'll show you how to reflect a function across the y-axis, the x-axis, what it means to reflect a function through the origin, and then how to classify a function as even or odd and what those symmetries look like graphically. So for our first example, we're going to look back at the W shape that we saw in the last video on transformations, and really a reflection is nothing more than another kind of transformation, a way that you can create a new function from old. So the first example, we're going to reflect across the y-axis, and the transformation that will achieve this is f of negative x. F of negative x will just take this initial function here and mirror it across the y-axis. You can see why if you create a table. If you create a table of values from the initial table of values that we have here, you can see that this transformation multiplies all the inputs by -1. So their sign changes. All of them were initially positive, so now all of them are negative, but if some were positive, they would turn to, some were negative, they would turn to positive. And if I just go and plot these new points, -1, 3, -2, 1, -3, 4, -4, 2, and -6, 4, you can see that the image that I get, it still maintains the general shape of the W. It's just been mirrored across the y-axis. So if you're mirroring a different function from our library, you just want to imagine sort of folding the paper in half this way and what it would look like. In our next example, we're going to reflect a function across the x-axis, and the transformation that will achieve that is negative f of x. So what I'm going to do in my table here, my x's and my new y's, so the x's will be unaffected, but the y's now will be multiplied by -1 because the minus is on the outside. It'll affect the outputs, just like with transformations. So because all the y's were initially positive, they are now negative. And if I were to go plot them, 1, -3, 2, -1, 3, -4, and 4, -2, and 6, -4, you can see once again the general shape is maintained, but now it's an M because it's been mirrored across the x-axis. This time you just imagine folding your paper that way. When we talk about reflecting through the origin, the transformation that achieves this reflection is really just a combination of the other two, making the inputs negative and making the outputs negative. And you can think of it as a two-step process if you want. But there is another way to think about this reflection through the origin. Clearly if I were to make the table, well, okay, if I make the table, both the x's and the y's become negative. But there's another way to think about this transformation as well that's pretty useful. Imagine that the origin was like a funhouse mirror. So not just a regular old mirror, but this point or this ball that's hanging in the middle of the funhouse. And what happens when you look into the mirror, your image as some sort of hologram shows back up on the other side, right there. And if you did the same thing with this point, that point were to look into the mirror, his image would show up on the other side here. You can kind of see where this was going. If this point were to look into the mirror, it would show back up over here. And if this point were to look into the mirror, it would show up over here. And if 6, 4 were to look in the mirror, it would show up over here at -6, -4. And you see that that's the same effect as mirroring the function about the y-axis and then about the x-axis. Or if you prefer, x-axis first, then y-axis first. The order wouldn't matter there. And it's the exact same result as you get your tables. That's how you reflect a function through the origin. Okay, in the next part of the video we're going to talk a little bit about what it means for a function to be even or odd and how that relates to the reflections that we did in the first few examples and some symmetries that we show in our functions. So first of all, a function is classified as even if f of negative x is equal to f of x. So this is clearly related to the first transformation that we saw where we mirrored about the y-axis. Basically what we're saying is a function is even if it's the same on both sides of the y-axis, if it's symmetric to the y-axis. So another way to say this, this definition, we can say if the point AB is on the graph of f, so is the point minus AB. Okay, and that's true for all x's. F of negative x is equal to f of x for all values of x, not just for one or two that you might happen to pick. Meanwhile, a function is classified as odd if f of negative x is equal to negative f of x. So what we're saying here is there's this relationship between the two transformations both happening. What we're saying about odd functions is they have that symmetry through the origin. And what it means is if the point AB is on f, so is minus A minus B. Okay? And remember that AB doesn't necessarily need to be two positive numbers, just like minus A minus B doesn't have to be two negative numbers. Just we're saying the signs are opposite. Meanwhile, a function is classified as neither if it's not even and it's not odd. So any other situation. Not every function has a symmetry. Not every function is going to be either or odd, even or odd. It could also be neither. So let's take a look at a couple examples and show that they're even or odd or neither algebraically and see what that means graphically. Example 4, take this function given here and figure out whether it's even or odd. First I'm going to do it algebraically and then I'll support my answer with my graphing calculator. So to determine even or odd neither, we just do this little test where we input negative x. Okay, we input negative x, and what that means is this function will change because instead of x cubed you'll have minus x cubed, 8 times minus x, and so on. And what you have to do after you input the negative x is you have to try to do a little bit of algebra and see where it takes you. So you think about what happens if you cube a negative. Well, when a negative is cubed or raised to any odd power, that negative is maintained. And if you multiply two minuses here, you get a positive. Meanwhile, in the denominator, if you square a negative, the negative is not maintained. So you have this function. And after every step that you do algebraically, you want to look back to your original and say, is it the same? Is it different? Where could I go from here? So I see it's not quite the same. I'm going to see if I can manipulate it in another way to find out what's going on. So I notice that the denominator is the same. I'll keep that. The numerator doesn't look the same, so I can try a little trick where I factor a negative 1 out of the numerator. And what you're left with after you factor negative 1 out of the numerator is x cubed minus 8x. And of course we know that when we're dealing with fractions, or in this case a rational function, it wouldn't matter whether we write our minus sign in the numerator like that or right out in front of our fraction bar like that. So what I managed to do was I managed to write f of negative x as negative f of x, and therefore I can say that f of x is odd. I got the exact opposite of what I started with. What does that mean graphically? Well, supposedly it means that if AB is on the graph, so is negative AB. So I'll get my calculator out, and you can do this along with me if you want. Change your batteries maybe. So in y equals, I'm just going to type x cubed minus 8x. Let me try that again with parentheses this time. X cubed minus 8x divided by x squared minus 9. And I'll take a look at a graph. And I'll see if I should adjust my window at all. Oh, look at that crazy looking graph there. So what I see here is there's symmetry going on to the origin. And that's the definition of an odd function. It's symmetric to the origin. You know, there's a point here that's mirrored over there. It looks like there's even asymptotes that are mirrored. So I can be certain that the work that I did algebraically is correct. Okay, one last example. Determine even, odd, or neither for this function. So we'll try the same exact test. F of negative x it's going to give me the absolute value of negative x cubed minus 5 times negative x, and then minus 3 times negative x squared. And then I go through and I try to see what I can do with that. A negative being cubed, the minus will be maintained. Uh-oh, better hurry up. Plus 5x, and then minus 3x squared. Because when you square a negative, it isn't maintained. Okay, now I look back at my original, and it's not exactly the same. This part's the same, but the part in the absolute value isn't the same. So I'm going to try to factor out that minus 1. So it'll look like this. Minus 1 times x cubed minus 5x minus 3x squared. And, of course, product of absolute values could be rewritten like this. X cubed minus 5x. And we know that the absolute value of negative 1 is just positive 1. So I'm back exactly where I started. And because I'm back exactly where I started, I can say the function is even. Let's see if our graphing calculator supports that. So in y equals, I'm going to type the absolute value. And to get to the absolute value, you want to press the math key. The math key is hiding here on the left-hand side, 3 spots down. Move over to num for number, or numeric operations, I forget which, and choose abs. So we got the absolute value of x cubed minus 5x. Now my phone's ringing. I'm not going to answer it. Minus 5x minus 3x squared. And we'll look at a graph. And there we see that nice even symmetry that we expected to see with our even function. So that's it for this video. Maybe I can get over there and answer my phone in time, or I can call the person back. But just so you know, reflections and even and odd functions.